Hello and welcome back to Math 241. We're still talking about functions from section 1.1. We're moving on to objective 2, learning objective associated with piecewise defined functions. So our first video accomplished this. We're moving on to that one. Gain familiarity with piecewise defined functions. So we're going to jump ahead here a little bit. Here we are. So, also a topic you may have been exposed to in Math 111. Piecewise defined functions are still a function. They have to meet all the same criteria as a regular old function, except they've got something new going on, and that is that instead of a single formula that defines them, there could be more than one. So they're piecewise defined in the sense that they might be defined on one portion of the domain one way, another portion a different way. And there are lots of mathematical examples we could throw out here, but I wanted to give one where we actually see some context here in just a minute. So here's just a quick one to lay the groundwork. This introduces us to the bracket notation. So you can see the little curly brackets here. These are frequently used with piecewise defined functions to separate the two portions that are, quote, in charge, if you will. So we might see f of t equals t cubed all by itself. That would be a perfectly good definition for a function. This claims that the t cubed is only the part of the function that gets to process stuff when the value of t, so our input, is between -1 and 1. In this case, inclusive, so it could be equal to -1 or +1. So you might think about this as, if we're using another factory example, we have a conveyor belt that splits off in two different directions. So we have two different machines that might tackle this depending on what type of input is there. So if the input falls into one category, it gets funneled into one machine. If it falls into another category, it gets funneled into the second machine. So in this case, the way we differentiate is that if it's a number between -1 and 1, t cubed is going to be the expression that takes over. If it's a value that's greater than 1, then this other expression, 3 minus t, is how the output gets computed. So here are two different machines, t cubed and 3 minus t, as a part of this one big function process. So to trying out a few values, just to see how this function works in example. So if 0 was our input, so f of 0, usually we would just have to plug this in somewhere. And we still will, but our first strategy is to figure out which of these two domain definitions is met by this input. So if we have a value of 0, 0 is not larger than 1, it is between -1 and 1. So this must be the function that's in charge, which is great. That means we should take 0, cube it, and there we are, 0 cubed is still 0. So our input was 0, our output is 0. If we try again, and this time we do 4 as our input, now we again have to reevaluate this. We go back to our domains and we say, okay, is 4 between -1 and 1? Well, clearly not. Is 4 greater than 1? Yeah, I think so. So that must mean that for this particular input, 3 minus t is the piece of the function that's in charge. So 3 minus, okay, well we give it an input of 4, so 3 minus 4 is -1. Great. If we give this function an input of 4, its output is -1. Delightful. Okay, so we'll try another color. If we give it an input of -2, then once again, we have to go back up to our definitions and say, is -2 between -1 and 1? Nope. Is -2 greater than 1? Nope. That's kind of a problem. The only two places this function is defined is for those particular inputs. So -2 has nowhere to go. And it might be counterintuitive because you could look at these and say, look, I can cube -2. I can take 3 minus -2. Those are both real numbers. But we never actually get to that stage. Again, the factory analogy, they never even make it to the machines. The conveyor belts just sort of break because they don't know which way to funnel this input of -2. And whenever we think of something breaking, that's telling us basically that the function is undefined at that input. So f of -2 is not defined because we have no way to evaluate it in this function. So there's a quick abstract example of a piecewise defined function. Let's try it in context. So let's just say, for instance, we've got this company that's purchasing parts in order to make stuff. So it costs $4 in parts and labor to produce each of these items that they're making. And that's if they purchase fewer than 5,000 units. And then they've got some fixed costs. So this might be renting the facility, paying for labor, etc. However, if they buy all these parts to make the stuff in bulk, and in this case in bulk it seems to be defined as 5,000 or more, then it only costs $3 per unit instead. So it turns out that we can take this situation and model it with a function. The catch, though, is that a single expression is not going to do it. Because if we imagine the input here is how many items we produce, it's going to depend on how many we purchase. So depending on whether we purchase 5,000 or fewer, well, fewer than 5,000 technically, or 5,000 or more than 5,000, we're going to have two different definitions. So just to throw some notation on it, we're going to call monthly cost C, and we're going to say we produced X items. There's our input. And it looks kind of complicated, but let's break this down. Here's our piecewise-defined function. Again, it's one function with multiple rules that determine what goes on. So cost as a function of x is, here's our bracket notation, 4 times x. So this is the cheap option, or sorry, the more expensive option, fewer items purchased. There's our $4 per item purchased, and there's how many items we purchased. So 4 times x would be the total cost to purchase and produce X items. And then the plus 2,500 is our fixed cost. Regardless of how many we produce, we still have to pay our supervisors and operate the machinery and so forth, or pay for the facility perhaps. And then here's the thing that's new to piecewise-defined functions. We've got our limits on our outputs, on our inputs. Our X values, how many items we produce, is limited to, well, I think you'll buy into this. We're not going to produce negative items. So we're going to limit it to 0 at the bottom. And then it also tops out at 5,000. That's not because we're limited to how many we can purchase, it's just that we start getting a cheaper price per unit once we hit 5,000. So our first definition is between 0 and 5,000, and then here's our next one. If we purchase parts for enough for 5,000 items, we're going to get this rate. So the only difference in the expressions between top and bottom is that here our unit price is $3 per item, and $4 per item in the first case. So here's our buying in bulk option. $3 times however many items we produce, plus our fixed costs, as long as we're buying at least 5,000 items. So the actual question here, we could have made a question out of make a function, but the real question is, at what production level is monthly cost? Exactly 25,000. Now, just to put this picture in your head, I don't mean to imply that this was the easy part. This is definitely the hardest part of this problem, almost no matter what the following question was. The setup of this question from the written description is almost always the most challenging piece, so I don't mean to minimize that at all. Building a piecewise-defined functions from words is challenging. Nevertheless, here's our question. What production level is monthly cost? $25,000. So just to keep this in perspective as well, you've only got 2 values that can take on stuff here. You've got an x, which is an input. That's the number of items. We're not asking for 25,000 items. The other numerical value we keep track of is cost. And that actually is the 25,000 that we want. We wanted our monthly cost to be exactly $25,000, so mathematically we'd write that as C of x is 25,000. So here's the challenge of a piecewise-defined function. You've got 2 different expressions that are in charge here. So we really have to solve it for each equation. We have to set 25,000 equal to the first expression, 4x plus 25. And then we have to set it equal to the second expression, 3x plus 2,500. So we've got, fortunately, these are linear equations, which we're pretty good at solving. So just to follow this through, 2,500 would get subtracted over, and then we would divide by 4. So we'd have 25,000 minus 2,500 all over 4, and that should be 5,625. So there's a problem, though. This seems like a great answer, but remember that the 4x plus 2,500 piece of this function was only in charge when the outputs were between 0 and 5,000. So we're trying to assign an x value of 5,600 to this expression, but it wasn't in charge then. So actually there is no solution to that portion of this function. There will never be $25,000 associated with buying at the more expensive rate. So we have a second equation to solve. Hopefully there's something exciting here. So we run the same algebra on this. We take away 2,500 from both sides. We divide by, I guess in this case, 3. And that gives us a very slightly different answer, 7,500. Okay, well, we've got the same issue. Can we check this against the original? So this portion of the function is responsible for, oh yeah, okay, so if our x value was at least 5,000, then this piece, 3x plus 2,500, would be in charge. Great, 7,500 is bigger than 5,000. We should be in business. So at a monthly cost of $25,000, the company can produce 7,500 of these items. So this is sort of the reverse translation process. Now we took x equals 7,500 and turned that into the company can produce 7,500 items. Went from the math to the interpretation and context. That's our video. We'll have learning objective 3 when we come back for the next one.